Welcome to Lecture 8 for the course ECE 257A, Fault-Tolerant Computing. In this lecture, we will cover chapters 10 and 12 in the textbook. Chapter 10 deals with fault masking, and Chapter 12 deals with some specific techniques, including voting schemes for accomplishing fault masking. So let's start with this diagram that basically shows methods for fault avoidance on the left side and fault masking on the right side. And this diagram has a nice symmetry that shows the relationship between fault avoidance techniques and fault masking techniques. Fault avoidance can be done through quality assurance. We basically prevent the occurrence of faults, and therefore our system will be perfect to begin with, and therefore we don't have to worry about faults. Or through fault removal, which involves testing. So we do testing. We either miss the fault, in which case our system will be faulty, so there will be fault inside, but we missed it, we didn't detect it. If we detect the fault, we have two options: repair the fault or discard the entire circuit. Excuse me. Discard it. And repair can be full or partial. With full repair, basically the circuit is brought back to its original condition and therefore it's fixed. With partial repair, the system will be partially repaired, but it will remain injured, so to speak. It's not completely back to normal condition and may still have some problems. On the other side, masking, we can use dynamic redundancy or static redundancy. If you use static redundancy, the fault is concealed so that it's there, but we don't see it. We don't see the effect of fault, and therefore the system operation is unaffected. See, this is the symmetric, the counterpart of this prevention on the other side. On the other hand, we may expose the fault rather than conceal it through monitoring. We monitor, and when we monitor, we may miss the fault, in which case the system remains faulty, or we can detect the fault. And when we detect the fault, we have two options: abort the computation, in other words, give up. The system will be faulty, but at least safe, because we abort the computation, therefore we don't use the incorrect result of the faulty computation. So we call this faulty safe. System is faulty, but it's safe. Or we reconfigure the system. We sort of do things to get around the faulty components. And the reconfiguration can be full, in which case the system is restored to its original function, or it can be partial, in which case the system may be degraded. As I mentioned, this diagram is completely symmetric, shows that for the methods on this side, there are counterparts on this side, and the relationships are very similar. Okay, the first idea in masking faults is the idea of interwoven redundant logic. And this idea is quite old, from the 1960s. So because in those days hardware was pretty expensive, this was sort of a curiosity because it involves a lot of redundancy. But now with nanoelectronics, people are taking a new look at this method, because with nanoelectronics, we can afford to have 8-fold, 10-fold redundancy. It won't be very expensive. So what's the idea? Look at this circuit consisting of alternating layers of AND and OR gates. There are two ANDs here, a single OR in this layer, and another AND in this layer. And these ones and zeros are basically signal values at the present time. And according to these signal values, the output is 0. Okay? Now suppose a fault develops in the circuit so that B, instead of being 0, becomes 1. So for example, this line is stuck at 1, using the terminology from the last lecture. If this line is stuck at 1, then the output of this AND gate will be 1 instead of 0. If this is 1, the output of this OR gate will be 1 instead of being 0. And two ones here will cause this final output to be 1. So we call such a fault a critical fault. It's a critical fault because this 0 changing to 1 affects the correctness of the output. Okay? Of course, critical faults should be avoided. But there are also non-critical, or sometimes called subcritical faults. Okay? For example, if C or D changes from 0 to 1, let's see what happens. If C changes from 0 to 1, nothing happens because 1 and 0 produces 0, and therefore the rest of the circuit, including the output, will be unaffected. So such a fault for this particular combination of input values is non-critical or subcritical because it doesn't affect the correctness of the output. Okay, so the lesson from this exercise, this diagram, is that even a non-redundant circuit such as this one has some fault masking capabilities. It can mask this line being stuck at 1 for this particular set of inputs. Okay, it cannot mask, however, this line being stuck at 1. So some faults are not masked, but some faults are masked. So even a non-redundant circuit has some fault masking capability. Okay, so the question is there a way to exploit this inherent masking capability of logic gates to achieve general fault masking? And the answer happens to be yes, we can do that. So here's the idea of what is known as quadded logic. Quadded means we basically use 4 times as many gates and 4 times as many signals to achieve fault masking. So let's see how this works. So this is the original circuit that I showed you before. And this is the quadded version of that circuit that has 4 gates for every gate in the original circuit. So this yellow AND gate there is replaced by 4 AND gates. And each of the gates has twice as many inputs. So this AND gate had 2 inputs. This one has 4 inputs. Okay, so it's roughly a factor of 8 in complexity because we have 4 times as many gates, and each gate has twice as many inputs. Okay, so each signal also has 4 versions. There are 4 lines that carry the same signal. So under normal conditions, the signals A1, A2, A3, A4, these are copies of the signal A, will all have the same value. So if A is equal to 1, all 4 copies normally have the same value. Similarly, E, which is 1 in this example, has 4 copies, and all of them will be 1s under normal condition. Okay, so let's see what happens if this A1, 1 copy of the signal A, changes from 1 to 0. Okay, if it changes from 1 to 0, the output of this gate changes from 1 to 0 because this gate has, both inputs are 1s, or in this case, all 4 are 1s, and therefore the output is 1. But if one of those changes from 1 to 0, this one also changes from 1 to 0. However, this fault, this change from 1 to 0 is masked by the OR gate, because this OR gate will receive a 1, another copy of the signal E is 1, and that 1 is enough to make the output of this OR gate 1, and therefore this one changing from 1 to 0 does not affect. So generally speaking, a 1 to 0 change is critical for an AND gate because only one change from 1 to 0 affects the output. But a 1 to 0 change is subcritical for an OR gate because it doesn't affect the output. Okay? And these alternating layers of AND and OR gates in the circuit basically convert a critical fault for AND gates to a subcritical fault for the next layer, which is an OR gates, and therefore masks that fault. As I mentioned, in the 1960s, this was a radical idea because so much complexity was sort of frowned upon because logic circuits were so expensive in those days. But now it's no big deal to have 8 times as many because each of these gates are tiny. Of course, we still have the problem of energy usage because if you increase the circuit complexity by 8, you will be using more energy. But if we manage to build nanoelectronic components that are very low energy, then perhaps the energy usage drawback will not be a major factor either. So this is known as quadrant logic. The more general name is interwoven redundant logic. The reason it's called interwoven is because of this pattern that you see here. So here I have A1, A2, B1, B2. So 2 copies of A and 2 copies of B go into this gate. 2 copies of A, 2 copies of B. 2 copies of A and 2 copies of B. And then the wires sort of are interwoven. In other words, here copy E1 and E4 of signal E are put along with copies F1 and F4 of signal F. And this is critical for this to function correctly. And so for these 2 gates, we have E1 and E4 and F1 and F4. For these 2 gates, we will have E2 and E3 and F2 and F3. Okay, so these wires are sort of interwoven, and that's a critical part of the design. Okay, so to mask H critical faults with this interwoven redundant logic, the number of gates is multiplied by H plus 1 squared, and the number of gate inputs is multiplied by H plus 1. So the special case of H equal to 1, we have 4 times as many gates and twice as many inputs. That's the special case of quadrant logic. But if we can afford higher levels of redundancy, then we can mask more critical faults. So H equal to 2 requires 9 times as many gates and 3 times as many gate inputs per gate. Okay, so this is basically a neat idea. It is, people are starting to use it, but not quite, it's not quite a mainstream idea yet. So here's an example of this in an actual circuit. So this is a half adder, A and B, sum and carry. And this is the same half adder built of NAND gates. And this is the quadrant version of this circuit. You see here this NAND gate, there are 4 copies of it over here. And these 2 NAND gates each have 4 copies. And then these inverters, each of them have 4 copies. So this is NAND gate used as inverter by feeding it with the same signal. Okay, so 2 inverters, 4 2-input NAND gates, 3 2-input NAND gates is this circuit. So you see it's significantly more complex, and you see that the connections are done in a special way in order to make sure that critical faults in one layer are converted to non-critical faults for the next layer. Okay, the next idea is something that we have looked at before. That's the idea by Moore and Shannon from the 1950s to build highly reliable logic from crummy or highly unreliable relays. So this is a little bit more detailed than our previous discussion of the same idea. So let's go into the details. So we have 2 types of relays in relay circuit. Of course, in those days, we still didn't have transistors. So relay circuits were used for control circuitry and telephone switching systems. So a relay is of 2 types. A relay can be normally open, and then if you assert a signal here, the relay will close. So this is a normally open relay that closes when you put in a logic signal 1 here, when you assert the signal into this. So this magnetizes basically this area, and then it pulls the relay down and closes it. And this is a normally closed relay that can be opened by asserting this signal. Okay, so of course a normally open relay should be open. If it closes, then that's considered a fault. A normally closed relay should be closed, and if it opens without the assertion of the signal, then that's a fault. Similarly here, if this closes without the assertion of the signal, that's a fault. So let A be the probability that contact is made given that it's energized. So if you energize it, the probability that contact is made is A. So A is, for a reliable relay, fairly close to 1. So with 99% probability, it closes when you energize it. But with a small probability, 1 minus A, the contact will remain open even though you have energized the relay. Similarly, C is the probability that contact is made when the relay is not energized. And 1 minus C is the probability that contact is open when it's not energized. So in a make contact, the contact of this type, A will be much greater than C if it's reliable. And for a contact of this relay of this type, A will be much smaller than C. Now, Moore and Shannon basically said it doesn't have to be. A does not have to be much less than C. As long as it's just below C, then we can synthesize relay networks, such as this one, that are more reliable than the individual contacts. And if this is more reliable than an individual the single contact, then you can use this now recursively as a contact and replicate it 4 times to get an even more reliable relay circuit. So that's the idea. So the idea was that no matter how crummy the relays, in other words, how close the values of A and C, one can interconnect many of them in a redundant series parallel structure to achieve arbitrarily high reliability. So in this particular example, the probability, the probability that connection is made given that the relay, so all 4 of these relays are controlled by the same signal X. So if X is asserted, then all relays should close, so contact will be made between the 2 sides. Now, if one of these relays is faulty and it doesn't close when X is energized, when X is asserted, then still connection will be made between the two sides. That's the idea. So we can easily derive the probability that connection is made given that relays are energized to be 2a squared minus a to the 4th, where a is the parameter defined up there. And this will be greater than a. In other words, this structure, this combination will be more reliable than a single relay if a is greater than 0.62. In other words, as long as the reliability of a relay is greater than 0.62, which is basically a very minimal requirement, the relay does not have to be very reliable, then this structure will have higher reliability. And then, as I said, recursively applying the same idea will make this more and more reliable. Probability that connection is made when the relay is not energized, that's undesirable. When the relays are not energized, we don't want connection to be made. That's 2c squared minus c to the 4th. And this is provably always less than c. In other words, that unreliability is always reduced, and therefore this is the essence of the method proposed by Moore and Shannon for building highly reliable relay circuits. Okay, the next idea, which is probably the most useful, the most commonly used nowadays, is triplication with voting. So if you want to compute a particular logic function, you use 3 units to compute it 3 times, and then the majority of these results will be taken by this voting unit and sent to the output. So if these two compute 1 and this one computes 0, 1 is in the majority and 1 will be output. So this one basically masks a single faulty unit. So if this unit 3 is faulty and it generates 0 when it should produce 1, the other two will produce 1s and the output will be 1. So this is basically a 2 out of 3 structure. As long as 2 of the 3 work correctly, we get the correct output, assuming that the voter is perfect, okay? We'll come to that later. What happens with an imperfect voter, we'll discuss later. So this is the reliability of a 2 out of 3 structure, each of the units have reliability Rm, module reliability. This is reliability of the ensemble. Okay, under what condition this reliability of the ensemble is greater than module reliability? Well, when the reliability of the module is more than 0.5. So this is TMR reliability, this curve. It is better than single module reliability whenever module reliability is greater than 0.5. And in fact, it's worse than module reliability if the module reliability is less than 0.5. But of course, module reliability less than 0.5 is not of practical interest, so we don't worry about that situation. So module reliability will be very close to 1. We'll be operating in this region, and then TMR is much better than the simplex or single unit system. And this is just some algebraic manipulation. I've written this R in this form to emphasize the fact that R is Rm times this factor. And this factor is 1 plus something. Okay? So as long as this something is positive, if this something is positive, then we have gained in reliability. Under what condition is this factor positive? When 1 minus Rm is always positive. We don't worry about that. So when 2Rm minus 1 is positive, And that leads to Rm greater than 1/2. Okay, now reliability of TMR is better. So if these are exponential, if Rm is e to the minus lambda t, then this is the reliability of module, the blue dash line. The red line is the reliability of the TMR structure. Again, you see that at some point the TMR structure becomes less reliable, but that happens, over a long period of time. That is not of interest to us. We are usually operating around this area where lambda t is small. In other words, remember that lambda is the failure rate. 1 over lambda is mean time to failure. And we are operating in time scales that are much less than 1 over lambda. So TMR is more reliable. But right here, I'm going to mention that TMR, even though it's more reliable in the short term, it becomes less reliable over the long run. So if you compute its mean time to failure, its mean time to failure is 5 over 6 lambda. The simplex mean time to failure is 1 over lambda. The TMR mean time to failure is less. That's because, mean time to failure is basically the area under this curve. And because this drops, and then it will be lower for a long period of time compared to simplex, the area under the curve is less, and therefore mean time to failure is less. So that's another indication that mean time to failure is not really a good measure to compare two systems, because you see the system which is much more reliable in practical terms for short duration of time actually gives you a smaller mean time to failure. So if you compare mean time to failures, then this simplex is better. Okay. So this is an example of triplication with voting that has actually been used in practice to protect against radiation. So if you want to build a flip-flop and you're worried about, particles bombarding the system and sort of changing the contents of the flip-flop, you can triplicate the flip-flop. And then it's very unlikely that the radiation affects all 3 copies. It may sort of change the value in 1 copy, but the other 2 copies will be correct, and therefore you get, and this is voter. This is another interesting part of this diagram. Why is this a voter? Because if these 2 signals are zeros, both of these 2 signals are zeros, then the multiplexer selects this value. 0 will go, because 0 will be in the majority. If both of these are 1s, then 1 will be sent to the output. If one of these is 0, the other one is 1, then the contents of the third flip-flop. So 1 and 0, so whatever this one shows will be in the majority. So this is basically a simple design for a voter. It's a 4-input multiplexer with the two control signals, select signals, connected to 2 inputs, and the third input goes to these 2. Of course, if you're worried about the radiation, it's completely possible that the radiation affects this voter, and therefore the system is not totally protected against radiation. It's protected if radiation affects the flip-flops, but not if it affects the voter. One way around this is to triplicate the voters. So what happens here if, so these are the 3 flip-flops. 2 inverters are basically form a flip-flop. 1 flip-flop, 2 flip-flop, 3 flip-flops. And then if radiation affects one of these flip-flops and the output is different from the other 2, there are 3 copies of the voter that basically correct the content. So 0, 1, 1 input to this voter produces 1 and changes that 0 back to 1. And therefore now if the radiation sort of affects this voter, it's no big deal because that voter only affects the contents of this one flip-flop. The other two will still be correct. So this is basically, this is capable of masking flip-flop faults or these voter faults, but of course it's a little bit more complex than the previous circuit. We can generalize this triplication and voting to what is known as n-modular redundancy. So for example, I've shown here a 5-fold redundant system with a voting unit. Here we can mask 2 faulty units because let's say if the first 3 generate 1 as output and these 2 are faulty, so they generate 0, 1 will be in the majority and therefore correct output will be produced. So the triplication, we called it triple modular redundancy. And this one we call it 5 modular redundancy. And more generally, we have n modular redundancy or NMR. And n does not have to be odd because you can have n equal to 4 and then you expect 3 units to agree. So 4 modular redundancy can mask 1 fault. But it can also detect 2 faults. In other words, if you have 4 modular redundancy and these 2 produce 1s and these 2 produce 0s, you can detect that. So 4 modular redundancy is capable of masking 1 fault, but it's also capable of detecting 2 faults. So typically n is odd, but it doesn't have to be odd. Okay, so this is basically a summary of these redundancy techniques that we have seen so far. We have duplication. In duplication, we have 1 active unit and 1 spare unit. The active unit is running under normal conditions, and its output is monitored by some detector that is in charge of detecting problems in this output. Now, how it detects it, there are various methods. We can use coding methods. We can use a watchdog timer. For example, if this takes too long to respond or something like that, then we sort of guess that something is wrong with it. We can also use duplication and comparison. So there may be 2 of these units actually operating concurrently, and the detector basically is based on comparing the 2 outputs. So if this is duplicated and this is also duplicated, that method is known as pair and spares. So we have a pair of active modules. We have a pair so that we can detect problems. And then these are 2 spares that take over. Now, when we say take over, there are various things that we can mean by that. So the spare can be, for example, powered off and just sitting to the side so that when this one is judged to be faulty and is removed, we sort of power up the spare, initialize it. It takes some time in order to bring it into service. So this is sometimes referred to as cold spare or cold standby. So we have an operating unit and a standby unit that is cold. In other words, it takes a while for us to bring it back, bring it into service, okay? We can also have a hot spare. A hot spare is operating concurrently with that. So even though we don't use the output of the spare, it's running as if that it's being used, just so that whenever we need it, in very short uh, time period, we can bring it into service because it's already running, it's already powered up, it's already in the proper state, it's already initialized to the appropriate state. We quickly bring it into service. Intermediate between cold and hot spare, we have something called warm spare. A warm spare may be powered up, but it's not completely up to full speed. It's powered up, but maybe it needs some initialization in order to be able to replace this unit. So we have cold spares. Cold spares basically save energy because they're not powered up, but they imply long delays when we need to bring them into service. Hot spares are running in parallel with the functional unit, and therefore they're ready to take over on very short notice. And warm spares are intermediate between these two. Okay, the triplication and voting masks the fault in place. So if this unit 2 is faulty, its output is masked. It doesn't affect the system output. And then we can use a combination of these two known as hybrid redundancy. So what is hybrid redundancy? We have 3 operational units that are capable of masking one fault. Now the problem with masking the fault is that we have 2 good units and one that is faulty. What happens if one of these good units fails subsequently? Then we can get an incorrect output. So this is basically not tolerant of 2 faults. If we have 2 faults, then we may produce an incorrect output. So this one basically removes the faulty unit because we know which one is faulty. We know which one disagreed with the other 2. Removes it and brings the spare into operation so that we are essentially sort of refreshing the system. We will have 3 correctly functional unit after we replace the faulty unit with a good unit, good spare. And this extends the life of the system because now, again, we can tolerate one more fault, and therefore the system can run for a longer period of time without generating an incorrect output. So this requires us to design the switch. The switch basically forwards 3 of these outputs to the voter. Initially, the 3 outputs that are forwarded are these 3, the top 3. But when we detect that this one disagreed with the other 2, then it will forward this one, and this one. And then, meanwhile, the system can continue operation as we bring this spare unit up to speed because we still have 2 good units. So we can take our time. We have more time to bring the spare. So this delay that was a problem up there does not exist here. The delay is masked because there are 2 good units running. As long as it doesn't take too long to initialize and bring this unit up to speed, we are going to be okay. Okay, of course, we can have more than one spare. And then once the spares have been exhausted, so suppose in this case we have one spare, this one is faulty, we remove it and bring the spare in. Now the spares have been exhausted, we don't have any more spares. So at that point, the system becomes static, becomes like this one. Okay, and no longer can bring other spares in. If we had 2 spares, then we could continue with 2 steps. Bring the first spare in, then upon the next fault, bring the second spare in. At that point, spares have been exhausted and we go to static redundancy. So hybrid redundancy becomes static once all the spares have been exhausted. Okay, and modular redundancy. Oops, I'm going backwards. So these are advantages and drawbacks of these 3 schemes: dynamic redundancy, static redundancy, and hybrid redundancy. Dynamic redundancy uses less power. It provides long life, especially if you have more than one spare, because basically we are using the units consecutively. If this spare is powered down, then it's less likely to fail. And therefore, once this one fails, we bring this one in and so on, so it can have long life. On the other hand, the problem of coverage that we discussed before is an issue here. There is a non-zero probability that we cannot successfully recover from fault in this unit and start operating this one. Either detection is imperfect, or even if we detect, switching is imperfect. So coverage factor is an issue there, and there's a latency involved in tolerating the fault. This one has high safety. It has immediate masking with high safety. It has power and area penalty because 3 units are running concurrently. So we have the complexity of 3 units plus the power usage of 3 units. And the voting circuit here is critical. If there's a problem in the voting unit, then we are in trouble. This one, basically, you can say has the advantage of both of those. It has immediate masking. It has long life and high safety, because the more spares you put in, the longer the life becomes. But then on the other hand, it also has the disadvantages of both of those. For example, it uses a lot of power. And now we not only have the voter, but we also have the switch. So the critical part of the system has grown in complexity. Okay, there are various ways of designing switches. So here is one approach to designing switches for standby redundancy. Here we have an active unit, and 2 spares. So this was basically a schematic diagram. We really don't have a switch like that. The switching takes place by an electronic unit that takes the output of these 3 units and then simply chooses which output to forward to the primary output of the system. Initially, it is this output that is forwarded, but then if this detector detects a problem in this unit, then it signals this problem to the switch, and the switch basically moves on and next will forward this signal to the output. Okay, and then once that one also is detected to be faulty, we move to the third one. So this switching here is electronic, not mechanical as suggested here. Okay, so how do we detect faults in such a standby redundancy scheme? We can have activity monitoring. So this detector is a monitor basically that monitors the output of this unit, and it has a bunch of criteria, a number of criteria that it uses to judge whether this output is okay. And we can use duplication and comparison. Of course, you know that detection in this scheme will not be perfect because this unit can generate an incorrect output that simply does not raise any flags in this detector. Okay, the duplication and comparison, you basically have 2 units here. They're both running at the same time, and we compare the outputs. The detector is basically a comparator that compares the outputs, and if they disagree, it signals disagreement or fault. And then we will see later in the next lecture, actually, that we can design these units to be self-checking so that they sort of signal any internal problems on their output so that the detector's job is simplified because the unit itself participates invalidating its output. That's called self-checking design that we'll talk about next time. Okay, let me skip this preview of self-checking design and go to switch for hybrid redundancy. So here is a hybrid redundancy method with 3 concurrently operating units and 1 spare. And this is more general. There are n concurrently operating unit and s spares. Now this switch, basically, one of the ways of designing it is a bunch of switches here in rows and columns. And normally, initially, when these are the active units, so these 3, for example, are active units, all these switches are set in the horizontal connection mode so that these signals are forwarded to this voting unit. Okay, so these 3 signals coming from these units are forwarded to the voter by these straight paths through the switches. Now, if one of these units is faulty and needs to be switched out, these switches can be reconfigured. For example, this switch set in this state will bring this unit to replace this last unit. So the last unit signal will go straight through, but it will stop here. Okay? Instead, the signal from this spare unit will be forwarded to the voter. So by appropriate setting of switches in this matrix, so the matrix will have n rows corresponding to the n active units and s columns corresponding to the s spares, and that's enough to be able to route the outputs of these spares to the voter instead of some of the active units. So this is one way of designing. So you see that this switch can be relatively complex. It will be an array of n by s of these 4-port switches. And therefore, the hard core of the system, the part that cannot malfunction, cannot fail, grows in size. That's one of the disadvantages of hybrid redundancy. Okay, another idea is to use time redundancy. So basically, we can say that this is redundancy in space because instead of just 1 unit, we are using, say, 4 units in this example. We are using more space. Okay, so redundancy is in space. Time redundancy is redundancy in time. So imagine if you want to compute sum of 2 numbers, okay? You use 1 adder. So in redundancy in space, you could use 2 adders and then compare the output. In redundancy in time, you can use the same adder twice. So add the 2 numbers once, store the result, add the 2 numbers a second time, then compare the 2 results. So this is particularly effective against transient faults. So if something happened in the first addition, but went away, some problem that went away, it was transient. In the second addition, then you detect the problem. Okay, if there's a permanent fault in your adder, then when you do the second addition, then you get the same wrong result. You may get the same wrong result because the fault is permanent. Therefore, you won't be able to detect that fault. So there are some techniques that make it more likely for you to detect even permanent faults. So for example, if you're using a multiplier and one of your operands is even, instead of multiplying a by 2b, this is the even operand, you divide this operand by 2 and multiply this operand by 2. This is basically right shift this operand and left shift this operand. And now you use the same multiplier hardware, but this time because the operands are different, it's unlikely for the same fault to produce the same incorrect result because different signals will flow through the circuit. And therefore, if something was stuck at 0, it's unlikely to affect the new computation in the same way as the old computation. So this is known with computation with transformed operands. So sometimes it's possible to change your operands. Another simple technique in addition is to just switch the operands. If you were doing A plus B, this time do B plus A. When you put B as the first operand and A as the second operand, you switch them. Then again, the internal signals of the circuit will change. And again, it's less likely for a fault to affect, to affect both computation at the same time. Okay, so there are a lot of tricks. So this is another one. Instead of adding A to B, complement A, complement B, and then complement the final result. So put the 2's complement of A in, or 1's complement, which is easier to compute. 1's complement of A in, 1's complement of B in. Do the addition. Again, the signal values change. And then form the 1's complement of the output. Okay, so this is the general method of computing with transformed operand, recomputing. So redundancy in time becomes more effective if you change the operands from one repetition to the next. Okay, another problem that arises when you have redundant circuit is that of testing. So suppose you have built this circuit that is triplicated and has a voter. Ignore this multiplexer here for the moment. And then you have built this unit and you ship it to the customer. But before you ship this, because it's sitting in the warehouse or on the shelf for a long time, one of these units, let's say, fails in the meantime. So you test this just before shipping to the customer. You input something, you see that there's a correct output, even though, because this is designed to mask the fault in one unit, you won't be able to detect that fault. So you're shipping basically a defective product to the customer that already has one fault, and the first fault that occurs after that leads to an incorrect output. And this is not what this unit is supposed to do. This is supposed to mask the first fault and maybe fail with the second fault. But if one of the units is already faulty when you ship your product, then this is not doing its job. Okay? So testing of redundant systems is harder. There's no way to test this because you just have one input and one output. So this is a structure that you can put in for the purpose of testing. So this goes with our discussion of testability in the previous lecture. So you basically have this multiplexer through which you can look at these outputs, okay? So you input something, and then you examine this output by selecting this, setting the multiplexer to select this one. You examine this output. So you make basically these points observable. They are not observable when you just vote, but through this method you make them observable so that if one of these is faulty, you observe the fault, and therefore you know that this unit is not okay. Okay, so these points that were not observable in the original design are made observable by adding this structure. Here are two well-known examples of application of n-modular redundancy and hybrid redundancy. NASA's Space Shuttle, which was retired in 2012, so it no longer exists, but the same redundancy methods are being used in other NASA spacecraft. So up to 2012, the Space Shuttle used 5-way redundancy in hardware. So the computer on board the Space Shuttle had 5 copies. Originally, in early shuttle designs, 4 of these 5 units were operational units, and 2 of them were spares. So this is a hybrid redundancy with 3 operational units and 2 spares. The 2 spares, one was warm, one was cold. In other words, one of them could be brought into operation more quickly than the other one. This one is there in case it's needed. Okay, it lengthens the life of the spacecraft computer. More recent shuttles in the latter stages of its life used 4 operational units and 1 spare. So this is again hybrid redundancy with 4 operational units. So this increases the safety when you have 4 operational units and it had 1 spare. It also used 2 independently developed software systems. So not only the hardware system was redundant, the software system was also redundant. Of course, in software, you can't use just 2 copies of the same software because whatever bug one copy has, the other copy will have also. So in the case of software, we use something called design diversity, meaning that 2 separate software design teams basically design the software from scratch so that they're unlikely to commit the same error, and therefore the software is unlikely to have the same bug in both versions of the software. Another example is the Japanese Shinkansen bullet train. It uses triple duplex system or 6-fold redundancy. Triple duplex means that there are 3 copies of a duplex system. Duplex system has 2 units operating in parallel, and comparison between the 2 outputs of the 2 units leads to fault detection. So you have 3 units, each of which is capable of fault detection, operating in parallel. And we vote on the outputs of those 3 pairs of units. Okay, let me now go to chapter 12 and get into some more detail about replication and voting. So this slide I'm not going to go through in detail. Basically is sort of a list of all the different techniques. The main points I want to make from this slide is that a typical digital system has a data path. This is where, inputs, numerical values or other types of inputs undergo transformations to generate output. A control unit that controls the operation of the data path through control signals and observe the state of the data path through these condition signals to see what's going on there and make appropriate decisions according to what's going on. And then some glue logic that basically connects these 2 together. Now, data paths are much more easier to protect against faults because they're more regular, and also because of the kinds of transformations that are involved here, they're easier to check. So here's a long list of methods for checking data paths. Control units are much harder to check because it's basically irregular logic. And the options are limited. Coding of control signals, control flow watchdog, and self-checking design. Glue logic is even more random in nature, and therefore self-checking design is basically our only option. So data paths are easier to check. We have a whole bunch of methods: replication in space, replication in time, and we discussed these before. Mixed space-time replication. I'll show you an example of that. Monitoring, but monitoring will have imperfect coverage. And also low redundancy coding. Okay, so the main point from this slide is that data paths present less of a problem in detecting and masking faults. Control units and glue logic are much more difficult to deal with. Okay, so here are some examples of replication in space that we have seen before. Some of these are shown in more detail here. So duplicate and compare is one method of replication in space. Triplication and voting is another method. Hybrid redundancy, in this example, 3 active units and 1 spare. And this is a method called pair and spare, where you have 2 pairs. Each pair does its own fault detection through comparison. And then the switch, basically, when this one does not indicate a problem, comparison basically indicates that the 2 match, may select this as the output. When these 2 disagree, then it may select this one as the output. So pair and spare is the name of this method. The Japanese bullet train used triplication, 3 pairs, okay? But this uses just 2 pairs. So these are examples of replication in space. Now let's look at TMR with imperfect voting. In the previous discussion, we assumed perfect voting. Now we say that the voter is imperfect, therefore it has reliability RV. So this is 2 out of 3 for the modules, times the reliability of the voter. And we are interested in finding out under what condition this overall reliability, RV times 2 out of 3, is greater than reliability of a single module. Okay, if you do the math, you basically discover that RV, reliability of the voter, must be greater than this function of Rm. And if you plot this, this curve is basically when these two are equal. Above this curve is when the R for TMR is greater, TMR is better. Below this curve is when simplex is better. And then the 2 axes, we have RM, module reliability, and voter reliability. So for a particular module reliability, let's say 0.75, and voter reliability 0.95, TMR will be better. Okay? Actually, if the voter reliability is 0.95, there's a range of module reliability values that cause TMR to be better. If you're outside that range, of course, this is not of practical interest because reliability less than 0.56 is really not good. But on the other side, if you have a voter whose reliability is 0.95 and a module whose reliability is also 0.95, then you don't want to use triplication because the TMR will be less reliable. Okay, so if the modules are highly reliable, you need highly reliable voter, even more reliable voter, in order to gain advantage from TMR. So this is interesting. So on the other hand, if you fix RV, RM must be between these 2 bounds. So that these are basically the 2 bounds here. For a particular RV value, there's a range of values for module reliability that ensures improvement in reliability. Okay, now when RV, when the voter reliability is pretty close to 1, let's say 1 minus epsilon, epsilon is a very small number, then 1 over RV here will be roughly 1 plus epsilon. So if this is 0.99, this will be 1.01. Okay, so 1 over RV is 1 plus epsilon. And then 9 minus 8 times 1 plus epsilon will be 1 minus 8 epsilon. And this, so the square root will be roughly 1 minus 4 epsilon. Okay, and then Rm, the range of Rm will be 0.5 plus epsilon. So these are approximate computations. The closer epsilon is to 0, the more accurate this. So this basically says if Rv is pretty close to 1, then as long as Rm is less reliable than your voter, and it's more reliable than this. Now this is pretty close to 0.5, so it's almost certain that you'll meet that condition. So as long as Rm is less reliable than your voter, then you gain with TMR. So this is in the special case where Rv is pretty close to 1. Okay, on Rm, the module being more complex than the voter, this condition is almost certainly met, and therefore TMR gives you an improvement in reliability. Okay, this one I'm gonna just explain. Won't go through the computation. The idea is that there are sometimes when you say if two modules here are faulty, then you get an incorrect output. That may be too pessimistic, because these two modules may be faulty in such a way that this output is incorrect, is stuck at 1, let's say, and this output is stuck at 0. So these are basically compensating fault. If this is stuck at 1 and this is stuck at 0 and this is correct, then this correct value will prevail, will have the majority, because it will match one of those faulty outputs. And you still can get, so under some conditions, you can have two faults and still get to the correct output. And these are known as compensating faults. If the faults are compensating, then you can get the correct output even with two faults. And this leads to reliability improving from this value to a little bit more. This is the added reliability. I'll let you read the details of this slide. So considering compensating faults leads to reliability improvement. Or actually not reliability improvement, but better bound for the reliability. Remember in homework 1, you did the reliability inversion problem. And so what we are establishing here are bounds, lower bounds for reliability, not actual reliabilities. But we get a better bound for reliability. Okay, replication in time. Of course, you can use the same unit twice. So here I've shown a computation on 4 inputs that involves 2 additions and a multiplication. Okay, once these 2 additions are done, the second computation, the replicated computation, can start while you're doing this multiplication. So you don't have to wait until this entire computation is done before starting the second version of the computation. And remember, the second version can have modified operands, not the exact same operands. So for example, you can switch the inputs to these adders. But let's ignore that for now. So the second computation does its additions while this first one is doing its multiplication. So we do a sort of pipelining. So instead of taking twice as much time in replication, it takes a little bit more. So let's say addition and multiplication both take 1 unit of time, just simplify. So this takes 2 units of time if you just did the computation once. If you do it twice, it takes 3 units of time. So it's not double the original. Now, in case you have just 1 adder rather than 2 adders, then this is the way you schedule the computation. Do the first addition. In the next clock cycle, do this addition. In the third clock cycle, do this addition. So it takes 3 time units. And this is a duplicated computation that takes 2 extra times. So we go from 3 to 5 time units rather than to 6, which would be with naive duplication. We can also do triplication with voting, the same computation that I showed you before. The first version of the computation, the second version, the third. So this one took 2 units of time, and the 3 take 4 units of time altogether. And then once we have the 3 results, we have to apply voting to get the majority of those. Of course, we can have a mixture of space and time redundancy. So for example, here we had 1 adder and 1 multiplier. When you add a second adder, you're basically using replication in space, and it takes less time now to do this computation. So here you had just replication in time, because you had 1 adder and 1 multiplier, no redundancy. Here you have 2 adders and 1 multiplier, you have some redundancy. So it's a mixture of space and time redundancy. Okay, this is one of my favorite topics because in my own research, I've considered the design of voting units. So this is the simplest possible majority voter unit design. So if you have 3 values on which you want to vote, you compare x1 and x2. If they agree, so this signal will be, if they disagree, the signal will be 1. So you use this, the third output. If they agree, then the signal will be 0. You use this one. So this is a voter that consists of a comparator and a multiplexer. Remember that when we do voting, these things on which we vote do not have to be just single bits. These can be words. So let's say these are adders, they add numbers, so these are the sums. So this is a 32-bit number, this is a 32-bit number, this is a 32-bit number. 3 versions of the sum. And then if these two match, they're the same values, this comparator determines that. If they disagree with each other, then this one is chosen. So we assume that we have just one bad unit. If these two disagree, then the bad unit is among these two, and therefore this one must be correct. If they agree, then both of these are good, then you can choose this one for the output. So this is a simple way of designing a voting circuit. And this is from a publication of mine from many years ago, in which voting units are designed in different ways and compared. So using gate networks, using multiplexers, 2 different designs. I won't go into the details because I have a different way of presenting this in a subsequent slide. Okay, and these are compared here with regard to complexity. The number of inputs, n, how many inputs you are voting on, and the total number of gates. And so this is the gate level design. The complexity is exponential. So pretty soon it becomes impractical. This is the multiplexer-based design. It grows less quickly, but still, after a while, with n 15 or more, it becomes substantial. Complexity becomes substantial. The other 2 methods, arithmetic method is based on basically counting the number of ones. Those of you who have taken my computer arithmetic course are familiar with the notion of parallel counters. A parallel counter basically counts the number of 1 among the inputs. So these 5 bits, we count how many ones there are among them, And if we find out that there are 4 ones, then obviously the output, the majority is 1. If there are 3 ones, then the majority is 1. If there are 2 ones, then the majority is 0. So that's the arithmetic. And then there's also the selection. If these are 1s and 0s, then the median of these values is also the majority. So if you have 3 1s and 2 0s, the median will be 1, which is also the majority. If there are 3 0s and 2 1s, then the median will be 0. So the other 2 methods in this diagram, the selection-based, which for large n is the best method among these, and then the arithmetic-based, which falls between selection and mux. So the gate level basically is not competitive for large n. These 3, selection is always the best method for large n. Next comes the multiplexer, the arithmetic-based method, and then the multiplexer-based method. Okay, more recently I've been looking into the some new technologies that are majority friendly. In other words, you can build majority gates in these technologies very easily. So the complexity of this majority gate, or 2 out of 3 gate, is not any more than AND gate and OR gate. So this is basically a 3 out of 5 voter using multiplexers, AND gate, an OR gate, and a majority gate. Okay, and this basically, this method is, I call it recursive method for designing voting large voters. This paper is not yet published. We are finalizing it, and it will be published soon. So once it's published, I'll add it to the references for this course. But for now, just take this. If I want to design a general threshold circuit that determines whether at least L of the n inputs are equal to 1. So 3 out of 5 is a special case of this. A 5-input voter, basically, we want to determine whether at least 3 of the inputs are 1s. In that case, then the output will be 1. Okay, so basically, recursively, we design the circuit by taking one of the variables and saying, okay, if this variable is 0, and I want at least L1s among the inputs, and this one is 0, then I must have at least L1s among the remaining n minus 1. If this input is 1, then I want at least L minus 1 ones among the remaining n minus 1 input. So this converts the design of this threshold circuit into the design of 2 smaller threshold circuits. And I can use this idea recursively, leading to a circuit such as this one. So this is X9, so that this is 9 inputs. This is a 5 out of 9 majority circuits. There are 9 inputs, and I want to determine whether at least 5 of the inputs are 1s. So X9 is used in this final multiplexer. X8 is used in these 2 multiplexers. X7 controls these. And then eventually I get to the edges where this is an AND gate. Okay, it's an AND with an inverter, so there's an AND gate. This is an OR gate, and this is a majority gate. Going back to the previous slide, basically we say if these 2, so this is a 3 out of 5. If these 2 are 0, if both of these are 0, then all 3 of the remaining inputs must be 1s. This is why I have an AND gate here. For me to have at least 3 1s, okay? These 2 are 0s. I need 3 1s among the remaining 3. On the other hand, if both of these are 1s, then I already have 2 1s. I need just 1 1 among the other 3 to exceed this threshold of 3. So that's why I have an OR there. On the other hand, in the other two cases, when one of these is 1, the other is 0, then I have 1, 1 here. I need 2 1s among these. That's why I have a majority gate here. Okay, so the same idea applies to this circuit. So this circuit has a nice regular structure, very VLSI friendly, easy to implement in VLSI. And we have shown that this has both lower complexity and lower power consumption than other ways of designing voting networks. Now, so far we have talked mostly in these detailed designs. These are bits. The inputs are bits. What about the inputs to the voting network are words rather than just bits? What happens then? Then we have to be careful. So here is, let me skip that first example, just go to the second example. So here are 3 words, 000, 101, 3-bit words, 110. Say 3 units generate these outputs. And I want to see whether there's a majority among those that I can use for the output. Well, if I use majority on individual bits, in other words, if I use bit voters, then I can get an incorrect result, because in this least significant bit, the majority is 0. In the middle bit, the majority is 0. In the most significant bit, majority is 1. So if I use bit voters on the 3 bits, I get something that doesn't make sense. It's not even equal to one of the inputs. Of course, in this case, I don't have majority because the 3 inputs actually disagree with each other. The 3 values disagree with each other. I don't have majority, but if I do bit voting, I'll be left with the impression that 100 has majority. But 100 doesn't even appear among the 3 inputs. So voting at the word level is different, and I need special design techniques. And some of those design techniques appear in this particular paper from 1991. Okay, these variations, I'm going to skip most of them. And if you are interested, please read them. Otherwise, just don't worry about them. They're not as important as the other things that we talked about in this lecture. So let me just spend a few minutes on this slide, which is the last one, to show one alternative to using, suppose you are doing, say, 16-bit addition, and you have a 16-bit adder. Instead of using the 16-bit adder twice to do the 16-bit addition twice and then comparing the result, one interesting alternative is to divide the 16-bit adder into 2 8-bit adders, the lower half adder, the upper half, and then input the lower halves of the 2 operands, compute the lower half, so you have 2 copies of the lower half of the sum, compare them. If they are equal, then you're okay. Save the carry, now input the upper half of the 2 operands. Use these 2 to compute 2 copies, and again compare. So this has the advantage that you're not using the same adder twice, but you're using the 2 halves. So these are basically different logic circuits. This is the first half of the adder, this is the second half, and therefore if one of these has a problem, this part of the addition will be performed correctly. Whereas if you use this, the entire circuit as a 16-bit adder, no matter which half you have a fault, you can get an incorrect output. So duplication in time would be more effective, less likely to lead problems if you use this scheme than if you just use the entire 16-bit adder twice. Okay? And of course, this can be done with triplication as well, which I'm going to skip. Okay, so that's all I wanted to say about fault masking and some details about design of switching and voting circuits. And please stay safe until we connect again in the next lecture. Bye for now, and see you later.